In this video, I'm going to explain how to write your first rstan program. So firstly, we're going to explain what model it is that we're going to be attempting to fit to some data. And the data that I'm going to use here is going to be fake data that I generate using R. Then within RStudio, I'm going to do the following sequence of things. Firstly, what I'm going to do in R, within RStudio, I'm going to use R to generate the fake data. Then, by creating a blank text file within RStudio and saving it as a .stan file, I'm going to then code up our model using the stan language. Then, using the R package rstan, which essentially is a way of connecting R with stan, I'm going to then compile the stan model from within R in RStudio. So the first step is just to compile the model. Then what I'm going to do is I'm going to use rstan to pass this fake data that we've generated to stan software. And after it has received the data, stan is then going to execute the no U-turn sampler for a given number of iterations. Then after stan has finished executing, it passes back important information that you need to do inference to R, and that information that we're going to receive is going to be information about convergence diagnostics and just general sampling diagnostics, and importantly it's also going to contain the samples for all our various parameters in the model. Importantly, in this video I'm not going to explain how to use posterior predictive checks to check that your model is actually fitting the data. And these are essential to do in any model building and fitting process. If you want to learn more about posterior predictive checks, I suggest that you look in my book or consult the stan website. There's a lot of information there. One other thing I want to say is that even though I'm illustrating this process for R and using the library rstan to interface with stan, the process is essentially the same within Python or MATLAB, say. Except obviously there are slight differences in the way that the data is passed and the commands that you use within the particular software that you're using. However, the stan code that we're going to use would be the same across any of these software. Now that I've explained the process, I want to introduce the model that we're going to fit using stan. So the model that we're going to fit is we're going to imagine that we have some data on individuals' heights, which I'm going to call here variable yi, where I here stands for the individual and y is just the variable containing their heights. And we're going to imagine that the heights are normally distributed about some mean, which I'm going to call here mu, and some standard deviation sigma. And so this is the likelihood for our model. We then, in a Bayesian framework, need to specify priors on our parameters. These are our parameters here, mu and sigma, that we're seeking to infer. And the priors that we're going to use here are mu is going to be normally distributed about some mean 1.7 and a standard deviation 0.3, and these are quite arbitrarily picked but seem fairly sensible. And sigma is going to be Cauchy distributed with a mean of 0 and a scale parameter of 1. And importantly, it's not exactly going to be a Cauchy, it's actually going to be a half Cauchy because of the fact that we are going to bound sigma at 0 in our stan code. However, the statistical details don't matter too much here. Essentially, all you need to know is that we've got a part of our model which is the likelihood, and we've got a part of our model which are the two priors that we're using. We're using independent priors here on mu and sigma. Now I want to illustrate how we actually go about this process in practice. So I've loaded up RStudio here, so at the moment everything's blank, I've just got a console here. So firstly what I want to do is to generate some fake data, and to do so I'm going to use R, so we need an R script. So I click up here in the top left and I select R script. Then what I'm going to do is I'm going to save that by pressing Control S or Command S on a Mac, and then I'm going to save it in some blank directory which I've just called first model 1 here. I'm going to call this s_first underscore model. And I normally put an S at the beginning of my scripts just so that I know that that's a script file. So if I save that, then what I'm going to do is I want to ensure that I'm in the right directory here. So what I'm going to do is I'm going to set working directory to the source file location, which then ensures that I'm in the correct working directory here because of the way in which I've saved this file. I'm going to put that at the top of my file just because I find that a useful command to sort of have at the top so that I always know that if I run that command, I'm going to be in the right directory. Then what I'm going to do is I'm going to generate some fake data. And I'm going to generate fake data using the same process that we use to model the data. So obviously in practice we don't generate the data ourselves, but here I just want to illustrate this process for some simple created fake data. So I'm going to assume that I've got a sample n of 100 individuals. I'm going to then generate some fake data of their heights, y, by using our norm, which is a random, or which generates random samples from a normal distribution in R. And the first input to this function is n, the sample size. I'm going to use a mean of 1.6 and a standard deviation of 0.2 here. So I can then, if I execute that, I get some fake data, which I can then look at a histogram of using hist_y. And you can see that has appeared down here in the bottom left, so I can sort of make that a bit bigger here by expanding this bottom panel here. But you see that we've got some normally distributed data, or approximately normally distributed data here that I've generated. The next step is to write stand code that allows us to fit the aforementioned model to this data. So to do so, I'm going to write the stand code within RStudio. And the way to do this in RStudio is you first of all create a blank text file by clicking the top left and then selecting text file. Then what you do is if you save that file as a .stan file, and what you should do is you should save it in the same directory as your script file. So here we have first underscore model.stan. If you do so, if you're using a recent version of RStudio, you should see that a stan icon appears here. And that's quite important because what this does is it recognizes stan syntax, which is really helpful when you're trying to write the model. Also, another thing that I like to do is to select this check on save option here. And what this does is it allows you, every time you save your stan code, it checks that your syntax is correct. So it can highlight any errors very, very quickly here. So I find that quite a useful thing to look at as I'm writing the model. So stan models typically involve at least 3 blocks. The first of these blocks is what is known as the data block, which is where you declare any data that you're going to pass to stan. The next block is the parameters of your model that you're actually looking to infer. The last essential block of typical stan programs is the model block, and you use the model block to declare the likelihood and the priors that you're going to use in your model. So you can see here that each of these blocks is contained within parentheses. So now if I save this file, hopefully what we should see here is that we get at the bottom here that our model first underscore stan is syntactically correct. However, we've got a warning message, which is that we've got an incomplete final line in our stan code. And the way to rectify this is just to put a blank final line at the end of your stan program, and then you'll stop getting that complaint down here. But it doesn't matter, your stan model will still compile if you have got an incomplete final line. Now what I want to do is I want to fill out each of these individual blocks. So what do we write in data? Firstly, we write the sample size. So here we've got an integer type variable, which is n, which is the count of individuals. Then we have a continuous variable. So a continuous variable in stan is what's known as a type real, and that is a variable y, but I've got that variable y for n individuals. So I'm now going to write n in square brackets, which actually says that we've got an array of heights of individuals, all of which are continuous. Then you can see here that in the first statement here, int n, I've put a semicolon at the end of the line. And any declaration in stan, you need to write a semicolon afterwards. And you can see that I've left it off here in my sort of real statement. And you can see that if I try and save this model, I then get a complaint down here in the console, which essentially is telling me down here, you can see that a parser expected a semicolon and it didn't find one. So that's actually a useful thing to know as you're writing a model. And so if I put a semicolon here and I clear the bottom and then I resave the model, then I get that the model is syntactically correct. So it all looks okay here. Next, I need to fill out the parameters block for our model. So first, I'm going to declare the parameter mu to be of type real, meaning that it's a continuous, unconstrained variable. Then, you might think that I can declare the variable sigma as also being of type real, but this would cause problems. And the reason that this is a problem is that the standard deviation sigma of a normal distribution can never be negative. So if I try and compile this model, I think that you get an error. So what you should do is you should declare a lower bound on sigma. And we say that the lower bound on sigma here must be 0, meaning that sigma is constrained to be non-negative. Next, after we filled out our parameters block, we need to write out our likelihood and our priors that we're using in the model. And fortunately, we can use essentially the statistical language that we use to declare our model to write out this model. And note that here I'm going to actually use a slightly inefficient way of writing out the model that doesn't use vectorization. But I think that for the first time that you're seeing a STAN program, it's better to see the model in full, and then you can use the kind of vectorization tips that I talk about in the book, and you can find on the STAN website. So here what we need is we need a for loop. So we need for individual I in 1 to n. We're going to assume that that individual's data yi, so that's the ith individual's height, y, and then you put square brackets around it, I, to indicate the ith component of the array, is going to be assumed to be, and I've got this sort of sampling statement here, this tilde, normally distributed about a mean mu and a standard deviation sigma. And I need a semicolon at the end here. So this statement here entirely defines our likelihood. Importantly, this statement here doesn't actually mean that yi is being sampled from a normal with a mean mu and a standard deviation sigma, but you can, at least in your first goes at coding up a STAN model, you can think about it that way. It just helps you to write out the model. Really what's going on behind the hood is that we're getting some sort of incrementing of the log probability here, but it doesn't matter too much for your sort of first go here. If you want more information about that, look in the book. So this is our likelihood. Now we need to code up the priors. And the priors that we're going to use here are those that we declared previously. So we're going to assume that mu is being normally distributed with a mean, which is 1.7, and a standard deviation, which is 0.3. And we're going to assume that sigma is going to be Cauchy distributed with a location parameter 0 and a scale parameter 1. And importantly, because of the fact that I've declared sigma as having a lower bound of 0, STAN essentially truncates this distribution, meaning that really what we're doing is we're sampling from a half Cauchy with these respective parameters. So now if I save the model, you can see down here that the model is being declared as being syntactically correct, meaning that it will compile. So now what I want to do is I want to go back into R, where I can actually use rstan to compile this model, which I can then run. So now what we're going to do is we're going to compile the model. And to do so, we need to load the package rstan. So in R, you just do that by doing library and then rstan. And you then load it, and you get a kind of typically a load of warning messages in my sort of experience here, probably because I'm not using up-to-date versions of packages. If you need to install the library rstan, importantly, don't just type in here the typical thing that you do in R, which is install.packages, because of the fact that you typically need to follow more rules in order to ensure that your installation is correct. And the best way to get up-to-date information on that is to look on the STAN website. You can also look at my book, but I recommend using the STAN website because it will contain more up-to-date information on how to install rstan. So we've loaded the library rstan. So then what we're going to do is we're going to compile the STAN model into an object which I'm just going to call here model, using the command stan_model. And then if you type apostrophes, you can then use autocomplete to find the model by hitting the tab. And here I can see that because I'm in the correct directory, I can see that model that I've just written here called firstmodel.stan. Then if you execute this command, you'll see that something's happening down here at the bottom. You get this kind of stop option here. And typically compilation of stan models can take anywhere from about 20 odd seconds on a new machine for a short model up to a few minutes on an old computer for a fairly long model. So I'm actually going to cut straight to after the model has compiled. So now the model has compiled, and so I can see that I've got this model object here in my global environment. Now what I want to do is I want to then pass the data to Stan and run the model. So to do this, I'm going to store the results, which are the diagnostics of the fit and the actual samples, in an object which I'm going to call fit. And then I'm going to use the command sampling, which is one of the rstan commands. And the first argument that you pass to that is the compiled model object. And the second command is a list with all your data in it, and it's a named list. So in R, what you need to do is you need to say, well, I need to pass it n, the first thing I declared in my data block, equal to n, that which I generated in R here. And then the second component here is going to be y. That's the second component in our data block that we defined in our stan code. And that's going to be equal to the y that I generated above here in R. Then I'm going to specify the number of iterations that I'm going to use, which is going to be 200 here. And I'm also going to specify that I use 4 chains. And it's important in whatever you do that I would say you always run at least 4 chains, because that gives you the best chance of diagnosing convergence. If you're on a computer that has multiple cores, which most do these days, then you can use parallelism to ensure that you are getting efficient use of time. So essentially what you want to do is you write a command in R, which is options, and then you specify the number of cores to use. And because I've got 4 chains here, I'm going to use 4 cores. So I then specify the command options mc.cores equals 4. If you don't know how many cores that your machine has, what you can do is it's a simple way to check, which is just by typing the command parallel and then 2 colons, because I'm going to look in the parallel library, and I'm going to use the function detect cores. And if you do so, it tells you the number of cores that you have available. So here you can see that I've got 8 cores available. Then what I want to do is I want to run the stan model. So I'm going to execute this command fit here. And you can see that down here we've got sort of information that we were starting 4 different workers here, 1 for each of the chains. And then because this model is really simple, it's gone through and it's just executed here. So you get some sort of information here that can be useful if it's got warning messages, for example, but here I don't really have any above here. Down at the bottom here, you often get these kind of warning messages that you're using a version of ggplot which isn't quite up to date. So I've got these kind of warnings here, but they're not actually something to worry about. So now our object fit contains both the diagnostics and the posterior samples that we've obtained using stan. So now what I firstly want to do is I want to diagnose whether or not everything's gone okay with our fit or our fitting process. So firstly, to do this, I typically do print fit. And what this does, as you'll see down here below, is that you get the sort of summary statistics for each of your parameters. So here we've got mu, sigma, and something else which is kind of like the log probability, but without the constants in it. And essentially here what you can see is, if I expand this window out a bit more, you can see hopefully that we've got, actually maybe I'll run that again, print fit. We've got our mean, standard error of the mean, the standard deviation, various quantiles. We've also got the effective sample size, which is pretty high for mu, a bit lower for sigma. You've then got the Gelman and Rubin version of R hat. Actually, it's the version of R hat which is in Bayesian Data Analysis 3. It's a slightly updated version of that. But here you can see that because each of these parameters is below about 1.1, then this is indicating in some way that we might have convergence here. Obviously, you're never sure in MCMC that you've actually got convergence, but here everything's looking okay. Above the kind of printout, what we have here is we have a bit of the information on the sampling. We can see that we use 4 chains, and each of the chains had 200 iterations. We also see that Stan by default uses half the iterations per chain as warm-up, and that means that after the warm-up we only get 100 samples, meaning that we get 400 total posterior samples. There's also a parameter thin here, which if you're running lots and lots of iterations and you've got lots of parameters, so you're running into memory issues, you can actually thin your samples here. Below the model here, we can see that it tells us which sampler we're using. We're using the no U-turn sampler, and it tells you the time and things like that. Then what I want to do is I want to actually extract the parameters and to graph them, or in other words, graph the posterior samples. So the easiest way to do that in R is to use the command extract. So I'm going to save the posterior samples that I have obtained via nuts here using in some object which I'm calling params. So I'm going to use the extract function, and I'm just going to call it like that. If I execute that, you can see that I've got this object here called params up in my global environment, and if you look inside that, you'll see that we've got 3 entries. We've got mu with 400 posterior samples, sigma with 400 posterior samples, and then this log probability but without the constants, which has also got 400 posterior samples. So if I then want to graph the histogram of the posterior samples, what I do is I look in my params file, and I then use the $sign to access mu, sigma, or the sort of log probability parameter here. So I can graph mu here, and we get out a posterior which looks something like this. And so it's sort of somewhere around 1.6, which makes sense because that was the parameter that we used to generate our fake data. Similarly, if I graph the posterior samples for sigma, we can see that we've got a sort of posterior, which is somewhere near the true value of sigma that we use to generate our data, which is 0.2. Remember that I'm using priors here as well, so those will actually move the position of the posteriors potentially away from their true values. But overall, it looks like we're doing pretty good at recapitulating the original parameters. Before I finish here, I want to show another way that you can diagnose issues with your sampling and graph your posterior samples, which actually saves on some of the manual work that I've just done here above. And to do so, I use the package rstan. So I need to load that package, and you need to install this separately potentially, although it might come as part of the new distributions of Stan included. So I just load that package, and I get a few warning messages out there, probably because I'm using an outdated version of ggplot. Then all I do here is after I fit the model, I just do launch rstan, and then I just pass it the fit object, which I obtained via sampling. And if I do so, this should open up your browser, whatever your default browser is. So here I'm using Safari, so it just opens up Safari. And don't worry, you don't need to be connected to the internet to use rstan. It just uses the browsing window as a way of displaying all the results here. So what you can see here is that it's loaded up a rstan interface, and this is for our model, which is called first model, which is what we save the Stan file as. And we've also got down here at the bottom 4 tabs, which are diagnose, estimate, explain, explore, and more, and they're also above here as well. So if we look in the diagnose tab, then essentially what this tab contains is it contains all the kind of information that you might need to diagnose if there are any issues with the sampling here. So I won't go into all of this in much detail, but essentially we've got some Markov chains, then we've got a histogram of our samples, we've got graphs of the posterior samples of mu versus the log posterior, we've got acceptance rates or mean metropolis acceptance rates as a function of the parameter mu. We've also got information on the sampled step size and also the tree depth, and tree depth is a parameter in the no U-turn sampler. And there's also other information here that you can access, and as I say, I don't want to go into that here, and there's a lot of information available on using this package online. There's also a tab here, HMC/nuts, which contains more of the sampling diagnostic criteria here in more depth. Importantly, we don't have any divergent iterations, so everything kind of looks okay with our sampling. We also get another tab here which is really useful, which contains, amongst other things, our any warnings that you might get on individual parameters for r hat. So it indicates if any of the parameters have an r hat which is above 1.1, None are in this case, so everything looks okay there. It's giving us a kind of warning for sigma that sigma might have a Monte Carlo standard error which is greater than 10% of the posterior standard deviation. So really what I should do is I should go back to RStudio and I should run the model for longer, perhaps 400 iterations, seeing as the sampling is pretty quick. And then I don't have any warnings here on the left which tell me about my effective sample size being low relative to the actual sample size. And you can change what the threshold warning level of each of these different criteria are here on the right. You also get autocorrelograms for the different chains, and there are 4 chains here, so I get 4 autocorrelation graphs per parameter. Here I'm just looking at mu. You can also look at the autocorrelation in a different parameter. Here, sigma, you can see that there is more autocorrelation in the parameter sigma. And this makes sense given that we think that sigma might be needing more samples here. So we can see that there's more autocorrelation here. So that's just a brief interlude looking at the diagnosis tab. The only remaining tab is this kind of posterior predictive checks tab. And as I say, I don't want to talk about posterior predictive checks here. If you want to know more about that, either look in the book or look on the STAN website. We've also got an estimate tab, which essentially, if you've got a number of parameters, it allows you to sort of look at box and whisker plots. I'm not quite sure what the name of these plots are. Essentially, it gives you, for each of your parameters, here I've got mu and sigma, it gives you a measure of their quantiles, which you can vary here. So you probably find that a bit difficult to see here, but there are kind of lines which are coming out here which are representing our posterior interval of choice. You also get posterior summary statistics, so you get that for all of the parameters in your model, which you also get via printing. It's quite useful here, you can actually download this, which is really nice, or you can generate a LaTeX table with these sampling statistics in them, which is really nice to include in papers. And I'll finish by talking about the last tab here, which is the Explore tab, which I actually find really, really useful when you've got problems with your sampling. So a really important thing here is if you've got 2 parameters, then you can look at plots of the posterior samples of one of the parameters against the other. So here we're starting off by looking at mu versus the log posterior. Usually not that informative to look at the log posterior plot, but if we look at mu versus sigma, the 2 parameters of our model, we can see here that there isn't much correlation between these 2 parameters, which means here that the parameters are well identified, and so it doesn't look like we've got any issues with our sampling here. The More tab contains things like the model code and other information that you can find here, but in all honesty I don't use this tab very often, so I'm not going to talk about that here. In this video I've illustrated how to code up your first model in STAN. In doing so, I've used the R package rstan to interface R with the STAN software. And I've done so within the kind of shell of RStudio. Importantly, if you use a different software to do the interfacing with STAN, say Python, MATLAB, Mathematica, etc., the code that you use to actually do the interfacing, so that would be here the compiling of the model and the parsing of the data to STAN, will differ between those different software. However, the STAN code itself is always the same. It's cross-platform, so it doesn't matter that you're using a different interfacing software. The STAN code remains the same. As I said here, I didn't illustrate how to do posterior predictive checking. This is an essential part of all modelling and should always be done when you're fitting a model to data. It's really easy to do in STAN, so if you want to know more about this, I suggest that you look in the book or you consult the STAN website.